I'll figure out a way to reward you guys for, but I will grade them. You will see them, and I'll give you some good points. So, yep. Okay, graphs of polynomials, first degree polynomials, something like this: y equals x. First degree polynomial looks like what? It's a line. Okay, and you can transform that line and do all sorts of different things. Second degree would be x squared. What does that look like? A parabola, and we know that you can shift that graph around and make it look like all sorts of other things. We've done that. Third degree is x to the third. And what does that look like? And again, we've said that you can change that shape, make it look all sorts of different ways. Fourth degree. What shape does that make? Kind of like a W. Could be upside down. Doesn't have to be. You know, some people look at that and they say, isn't that a parabola? Fourth degrees can also look like that. You might be missing some of the bumps in there, remember. And then fifth degree, you know, something like that. So, local extrema of a polynomial. Given a polynomial has degree of n, there are, at most, n real roots and how many bumps does this one have? None. This one? N minus 1 bumps. Sometimes those bumps are taken out by double or triple roots. What does a single root look like? Just passes right through. How about a double? Touches tangent, bounces off. Triple, flattens out, passes through. So you tell me this polynomial right here. Single, double, triple root. Single, double, triple root. So what degree polynomial do we think that is? 9. I would say that's probably next to the 9th. Now, writing an actual equation for that would be a totally different matter. We're not going to do that right now. We're not going to fill in all this. This is basically where they end and start. Remember, if they're positive, they finish up. If they're negative, they finish down. If they're even, they start and stop in the same. If they're odd, they start and stop opposite. Last piece here. Do you remember what the remainder theorem says? If p of x is divided by x minus a, do you remember how to tell what the remainder is ahead of time? You plug in what? Plug in a into the polynomial. If p of x is divided by x minus a, then p of a is the remainder. Does that make sense? We know how to use that, right? Okay. And last piece before we move to the backside is synthetic division. What goes here? A, or the root. What's the last box? Remainder. What goes up here? Coefficients, good. And remember that our results are our constant, our linear term, our x squared, our x to the third, our x to the fourth. We work backwards to list all of our coefficients for our terms. So the front side of the sheet was a nice summary of everything we really learned within the first 2 days. Hopefully helped organize our thoughts. I'm just giving you guys a quick run through that. I know you already know this content. It'd be really, really good if you glanced over it a couple times, if you kept it handy, and you just refreshed your brain with it before you take your next test. And we'll refer back to it. So always keep this out. Please look at the next sheet, just the back side of it. The very first time that I started teaching rational roots theorem, people didn't get it. Because I'm a bad teacher, I did not change anything the second time, or the third time, or the fourth time, or the fifth time. Finally, the sixth time, I changed something. I said, they didn't know what to do when. And I said, okay. And I'm actually adjusting this for next year now that I'm going to incorporate Descartes' rule of signs and other things as well. But we always start out with this process. Identify the number of roots. Does the polynomial factor? If it does, I have all the factoring methods that we've talked about listed right here. So you can... if you want to know about a factoring method, you can look at that. And we're going to use this in just a second. If it does not factor, we have to use the rational roots theorem. What's the first part of using rational roots theorem? What do you have to identify? P's and Q's. So identify factors of the constants, P's and Q's. List them as positive and negative as a ratio. After I list them, what do? Plug them in. Use synthetic substitution to plug them in. Find one that works. Once you find one that works, divide it out using synthetic division. Then look at your new polynomial. If it's degree of 2, then you factor, use a quadratic formula. If it's not degree 2, if it's degree 3 or higher, then you need to start all over. And so you go back to here. Doesn't necessarily mean you have to use a rational roots theorem again. Maybe you can go to a factoring method like grouping. Okay, keep this handy. We go to your notes for today, which are right here. Okay, this is very, very new material. I know that everything that you've seen up until this point is pretty much what you had last year. And I'm guessing that when we grade your test tonight, that they're going to go very quick, that you guys know exactly what you're doing. Okay, but Descartes' rule of signs. Descartes was a mathematician, philosopher, great thinker back in the Renaissance era. And he made some great contributions to mathematics. And this is one. And really, here's the question. You guys, when you do your guessing, let's say that the last number, you had x to the fifth, then you had 48 or 96 or something like that at the end. Sure is a pain to list all of those, isn't it? Sure is a pain to try to think of all the different factors that you could possibly have. And all of a sudden somebody sticks a 6 in front of that and you're like, oh my gosh. Well, Descartes ran into the same problem along with many mathematicians. And they said that there's a way we could be smart about what numbers we're choosing to use. We're going to learn to be smart today with the numbers that we're choosing. Descartes' rule of signs says as follows. The number of positive real roots. This doesn't say anything about complex or imaginary solutions. The number of positive real roots, or solutions or zeros, those are all the same things, of p of x is equal to the number of sign changes of p of x or less by a factor of 2. So that's for positive real roots. positive. Now we got negative. Negative real roots will be the same thing, but it's p of negative x, or less by a factor of 2. So now we're going to learn what that means. Okay, so this is new. That's what it says. We'll try an example. After we do the example, you go back and read it, and then it should be locked in your brain. Okay. So it says identify the possible number of positive and negative solutions of the following polynomials. So what I do is I look at my terms and my coefficients. Okay. Is 3x to the third positive or negative? It's positive, right? Okay. 3, no negative sign, so it's positive. Okay. How about the 4x squared, positive or negative? Negative. This one? Positive. This one? So look, do I switch sign from positive to negative from this spot to this spot? Yes. I switch. So that's one sign change. Do I switch from this spot to this spot? Yes. So that's a second sign change. Do I switch from this one to this one? Yes. That's a third sign change. So, positive, real solutions. I will either have 3 of them because there are 3 sign changes, or less by a factor of 2. So I would just subtract 2 from 3 and get 1. Let's suppose that there were 7 sign changes. Then the number of positive real solutions would be 7 or 5 or 3 or 1. Let's suppose that there were 177 sign changes. You just 177, 175, 173, so on and so forth. Now, that's positive. We just did p of x. Now I have to do p of negative x. So let's plug a negative x in there. If you plug a negative x in, what do you get out? Negative 3x to the third. Does the next one change? No, minus 4x squared. Minus 5x, minus 2. Are there any sign changes? No. So therefore, negative real solutions. There are none. So let's be smart about this. If you were using the rational roots theorem to find a root, would you try plugging in negative 2? Would you try negative 3? Would you try negative 1? Would you try anything that's negative? No, you know that there are no negative real solutions. Could you try positive 1? Yeah, you could try positive ones. Take out your calculator, let's graph this so you can see exactly what's happening. Yes. Hey, Chrissy. Oh, never mind. It turned on. Sometimes I have to turn it on using the computer. Okay. We put in our normal one, not the negative one, so 3x to the third minus 4x squared plus 5x minus 2. And I'm going to graph it in a normal viewing window. So zoom 6. And as you see what you get, as you look at that graph, how many times does that cross the x-axis? Once. Does it cross on the positive side or the negative side? So look, I have one positive real root. You can see it does not cross in the negative at all. So it does hold up to what we said it would. Second of all, how many solutions does this polynomial have to have? 3. So if we found 1, what are the other 2? We would see a triple root if it was the same. Good thought, but it's not the same. What are the other two? Imaginary. So we have one that's, so this only applies to real solutions. There are two that are imaginary here. There's one that's real right there. Maybe 1/2. Looks like 1/2 could be an option, or 2/3. And the other one would be imaginary. Okay, let's try the next one. How many sign changes do you see for that one? None. So how many positive real solutions are there? 0. If I want to find the number of negative real solutions, what do? Plug in negative x. And I get negative x to the 4th minus x squared minus 1. It stays exactly the same. How many sign changes are there? What is negative x to the 4th? Positive, and then you multiply it by a -1 on the outside. So you can see the 4th means you're going to have 4 negatives, and then a negative on the outside is your 5th negative. So you have negative real solutions. You can see that, again, you have no sign changes, so you have exactly 0 negative real solutions. If you have 0 positive real solutions and 0 negative real solutions, how many times does this thing cross the x-axis? None. It can't. It can only have complex roots. Because how many solutions do we know this thing has? 4. And if none of them are positive, if none of them are negative, then it must have 4 imaginary. And if you go to y equals and you graph this, negative x to the 4th, or you watch me graph it, minus x squared minus 1, and I graph it, you can see, does that ever cross? No, it does not. So therefore, you can see that it must have imaginary solutions. So once I test this, should I go about the rational roots theorem? No. That'll be silly. I can't come up with any rational roots. There are none. Okay. Second piece of learning, upper and lower bounds. Let's suppose that you had a 48 or a 96 on the end. Wouldn't it be nice to know whether or not you really need to plug in 96? Wouldn't it be nice to know whether or not you need to plug in, say, 24 or 8 or numbers that divide evenly into those? Those are really difficult. Well, there's a way to find out. There are upper and lower bounds, and here's what it says. If b is positive and you stick it into synthetic division, and you divide the polynomial out, and you get positive, 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 all positive results, then you know b is an upper bound. If a is negative, and you plug a in, and you get alternating signs as a result. It doesn't have to be plus, minus, plus, minus, plus, minus. It can be minus, plus, minus, plus, minus, plus. And you could even have a 0 in there. Then you know a is a lower bound. So let's look at the example. It says show that the polynomial right here has real zeros that lie between -3 and +2. If you were to use the rational roots theorem on this, what would be your p's? 1 and 5. What would be your q's? 1. Okay, so that's what you would try. And I'm going to tell you that you don't need to plug in 5. You don't need to try 5 at all. And we could show that 5 is not a realistic opportunity to be a root. Obviously, you could plug it in, but there's another way. And I know right now you're saying, well, why not just plug it in and save time? Again, instead of being to the 4th power, suppose it was to the 20th power. And suppose instead of 5, it was 192. All of a sudden, it becomes a lot more complicated, right? Well, we're going to show that all of the solutions lie between 2 and -3. All of them lie between here. And here's how I'm going to do it. I'm going to plug in 2 to synthetic division. I'll take that polynomial, I have 1, 0, -3, 2, and -5. What's my first step with synthetic division? Drop the 1. Multiply. What do you notice about the result that you got when you did synthetic division? All of these numbers are positive because all coefficients, rewrite that, sorry. Because all the coefficients are positive, 2 is an upper bound. So what does that tell us about the solutions? All solutions must be less than 2. If 2 is the upper bound, then all the solutions are less. So should I try plugging in 5? No, because 2 is an upper bound. Let's now show that -3 is a lower bound. You do the same thing. You plug it in. -3, 1, 0, -3, 2, -5. First step, drop down the 1, multiply. What do you notice about that result? The signs all switch, right? Alternating signs. Because the signs of the coefficients alternate. -2 is a lower bound, right? So all solutions must be greater than -3. Did I say -2 in there? Sorry. -3. I'm sorry. -3 was our lower bound. So all the solutions have to be greater than -3 because we saw alternating signs. So will you actually use this? Not necessarily. The upper and lower bounds I haven't used very often. Do I use Descartes' rule of signs? Yes. And you're going to be given 5 or 6 problems today to do as an assignment. We have 2 on the back side that will show you exactly what to do today. And you can go about your work. And we want to try to incorporate these when possible. So if you flip it over to the back side, the directions in your book will say, I typed it out exactly like they say. It says find all rational zeros of the polynomial. Then find the irrational zeros, if any exist. Whenever appropriate, use the rational roots theorem and upper and lower bounds theorem, Descartes' rule of signs, quadratic formula, or other factoring techniques. If able, sketch a graph. I didn't do that first hour, so we'll leave off the graph because I forgot to tell them to. So sorry. Here's what I want you to do. We won't necessarily always use the upper or lower bound piece, but we will do this. We will definitely use Descartes' rule of signs. There we go. First of all, how many roots are there to this polynomial? There's 3. Let's look at the sign changes. How many sign changes are there currently in that problem? 2. The first number is 1, then it goes negative, and then it goes from negative to positive. There are 2 sign changes. So, how many positive real solutions could there be? 2 or 0. Less by a factor of 2. Now let's identify p of negative x. If I plug in negative x, how does this change? We got negative x to the third minus 3x squared plus 13x plus 15. How many sign changes are there? 1. So negative real solutions, I would have 1. So some people looked at this first hour. They said, well, Mr. Gens, it's obvious. We have 1 negative real solution, and we're going to have 2 positive because that adds to 3. Not necessarily. You have to have 1 negative. We know that. But you could have 1 negative and 2 imaginary. So you either have 1 negative and 2 imaginary, or you have 1 negative and 2 real. I should start the rational roots theorem. If we start our graphic organizer that we talked about, as you look at that polynomial, does it factor? No. If it did, I would use one of these. It does not, so I use the rational roots theorem. I start by identifying my P's and Q's. What are my P's? My P's are 1, 3, and 5. What are my Q's? 1. If you take all of your P's and divide them by all the Q's, list your positives and negatives. Your choices for rational roots are plus or minus 1, plus or minus 3, and plus or minus 5. Those are your options. Oh, 15. Sorry. Thank you. Don't be afraid to speak up. Nice and loud, Billy Barber. Just as loud as you are at the beginning of class. I'm whispering. It's like we're teaching in a library. Don't disrupt anybody else. Okay. All right. What would you like to try? 1. Okay. So we plug in 1. If you plug in 1, you get 1 minus 3 minus 13 plus 15. 1 minus 3 is negative 2, minus 13 is negative 15, plus 15 is 0. So 1 is a solution. What do I do next? Synthetic divide. Drop the 1, multiply. Look at my result. Is 1 an upper bound? No. 1 is not an upper bound. Why? Right. So would it be good of me to try, say, 3 or 5 or 15 after that? Well, sure. It's not an upper bound, so I need a bigger root. So 3, 5, or 15 very well might work. Do I have to try the rational roots theorem again? No. This factors. I know 1 is a solution, so x minus 1 is a factor. And I have x squared minus 2x minus 15. How does that factor? So my solutions are 1, 5, and negative 3. Look at what we started off with, guys. We said we would have how many negative solutions? 1. We got 1 negative. Positive solutions, 2 or 0. We've got 2. It checks our work. We know we did it right. Great way to follow through. Any questions? This is a very helpful way to check your work, yes. The negative solutions, you got to plug in p of negative x. Got to plug in the negative x. And when you plug in the negative x, then you look for the number of sign changes. Okay, last one. This one's x to the 5th. Let's start with our sign changes. How many sign changes? 4. So how many positive real solutions might we have then? We might have 4, 2, or 0. Let's identify p of negative x. If we plug in negative x, we're going to get negative x to the 5th minus 3x to the 4th plus x to the 3rd plus 11x squared plus 12x plus 4. How many sign changes were there? 1. So negative real solutions. We have 1. Does it have to be 1 and 4? No, it could be 1 and 2 and we would have 2 imaginary, or it could be 1 and 0 and we have 4 imaginary. Does it factor? Doesn't look like it. I start the rational roots theorem. What are my p's? 1, 2, and 4. What are my q's? 1. My choices, plus or minus 1, plus or minus 2, plus or minus 4. What would you like to start by checking? You want to try 1? Okay. We don't do it to negative x. Remember, we do it to the first one. We try 1, and we get 1 minus 3 minus 1 plus 11 minus 12 plus 4. 1 minus 3, negative 2, minus 1, negative 3, plus 11, 8, minus 12, negative 4, plus 4, 0. So 1 works, yes? Oh boy. 1, negative 3, negative 1, 11, negative 12, 4. Drop down the 1, multiply. Are the answers all positive? No. So it's very possible that, you know, we would have another positive real root that's bigger than that. Can 1 happen more than once? Yeah, it sure can. Let's try it again. So my new polynomial is x to the 4th minus 2x to the 3rd minus 3x squared plus 8x minus 4. Let's try plugging in 1 again. You would have 1 minus 2 minus 3 plus 8 minus 4. What do you get? Yep, get 0. So let's divide 1 into that again. Drop the 1, multiply. Your resulting polynomial. Are all the answers positive? No. Now what do you want to do? Yes, we could group them. Very good. We could group them. They do factor. So I'm going to change this to plus, negative. So I can put my parentheses down. This does factor. What can you take out of the first part? X squared times x minus 1. What can you take out of the second part? Negative 4. You get x minus 1. What is the common factor? X minus 1 leaves you with x squared minus 4. Does that factor? Yep. X minus 1 times x minus 2 times x plus 2. Solutions are 1, 2, negative 2. How many total solutions were we supposed to have? 5. We have our 2 1s from the beginning, so we have 1, 1, 1, 2, negative 2. We have a triple root of 1, and we have 2 and negative 2. So if I would have started with 2, I would have come up with an upper bound, and I would have known that I could try 2 or 1 after that. But 4 wouldn't have been a solution. So, you know, did I actually use the upper-lower bound part when I was doing this? No, I didn't. So you might be asked on your test to do an example like we did in your notes to show that there's upper and lower bounds. But will you actually use it? That's kind of up to you. Look at our end result. We have 4 that are positive, 1 that's negative. If you go back up to our original, we have 4 that are positive. We have 1 that's negative. It all worked out. And so we checked our answer. We're good to go. Your assignment is section 3.3, page. Just have 6 problems, just like we did. The next section is on complex numbers. You guys are going to find that easy. It's like 1 day. Looks like we could have a test next week, Tuesday, I'm thinking. Friday? I don't think we're going to make it by Friday. Page 288, 65 through 70. But calculus will have their test by Friday, so. Yeah, we'll get to that's all we're doing. So complex or related rates that you guys are working on, that's it. Well, we'll extend a little bit tomorrow, but not much. I'm going to show you guys how to use some trig. So, do you want that? Okay, then let's talk about it real quick. Here's really all we did was this. If the function is positive, it ends going up, right? If it's positive, it ends up. So if you look here, if n is, so this is the degree, if n is odd, but the function's positive, as x goes to positive infinity, f of x goes to positive infinity. And if n is even, but it's positive, f of x also goes to positive infinity. Yeah. But the reason why we did it is so first I showed them that, but then I told them what it means. And basically all we said was this. If it's positive, it ends going up. If it's negative, it ends going down. Now, if it's even, they start and end in the same place, right? And if they're odd, they start and end in the opposite place. And that's all we did there. But that's the notation, Sarah, that's the notation that your book uses.